Welcome back to Control System Lectures. This is the second video on the root locus method. And in this video I want to show you a few of the rules that you have to follow in order to sketch a root locus by hand. But if you will, bear with me for a few minutes, because before we begin I want to make a case for why I think this is important, and hopefully put you in a certain mindset to watch this video. I'm sure there's a number of you watching this that are taking a control system course at a university. And you might have an exam coming up where you're going to be asked to sketch a root locus of a few systems. And certainly this knowledge is helpful in order for you to pass your exam. But is there a benefit also to knowing how to draw a root locus by hand as a practicing engineer? It's true, though, that most of the time you're going to be using a computer program to plot the root locus. And even then you don't have to calculate the gain at any given point, because in a program like Matlab, all that you have to do is click on the area of the locus where you want the roots, and it'll tell you the gain. So why are we worrying about learning how to draw a root locus by hand now, when in the future we're just going to be drawing root locus on a computer? Well, I think one of the strongest arguments for learning how to sketch a root locus plot by hand is this. Let's say that you're given this open loop transfer function, 1 over s plus 1 times s minus 2. It's quite clear from this transfer function that this system is unstable because there's a pole in the right half plane at s equals 2. So your job is to stabilize this system by wrapping a control system around it. Naturally, you start with the simplest controller, which is proportional control, and then you plot the root locus on a program like Matlab. And what you're going to find is a root locus that looks a little something like this. Now remember, you're trying to move the roots somewhere over to the left half plane, or that you want both roots to have negative real parts. But as you can see, no matter what gain you choose, the root that starts at positive 2 will always be on the right half side. And as the gain increases, the root that starts at negative 1 also goes unstable. So what can we infer from this? Well, we can't solve this problem with proportional feedback. It just won't work. So now you're looking at the root locus and you need to figure out where to put additional poles and zeros so that you can meet your requirements. But where do you add poles and zeros in the feedback path so that your root locus looks the way that you want? Or specifically so that your poles both go to the left half plane? Well, knowing how poles and zeros affect the root locus comes from understanding these rules about how to draw them by hand. And this makes control system design much easier. So the classic way to set up a root locus problem is like this, where the gain is in the forward path and you have a unity feedback. And when you solve for the closed loop transfer function for this system, you get k times g of s in the numerator and 1 plus k times g of s in the denominator. And since we're only looking for the poles of the closed loop system, we only care about the denominator, 1 plus k times g of s. And the poles of this closed loop system come when 1 plus k times g of s equals 0. And this is the basic form that we need the characteristic equation to be in order for us to use our drawing rules that we're about to go over. And like I said, this is sort of the classic setup that you would see in textbooks. However, if you use Matlab to draw your root locus, with its built-in function rLocus, it draws its control system slightly differently. The difference is that when you type rLocus of g of s in Matlab, it places the gain in the feedback path rather than the feed-forward path. But I'll show you when it comes to actually drawing a root locus, both of these methods produce the exact same plot. Again, we can draw the closed loop system for this transfer function as g of s divided by 1 plus k times g of s. Notice that the denominator is the exact same, 1 plus k times g of s. Exactly the way that we had it before, but we do have a different numerator. This just means that the system is going to behave differently due to forced inputs, which we don't really care about in this situation. But if you did want exactly the same transfer function in both cases, you could just multiply the input by k to make these equivalent systems. Either way is fine though, because from a stability standpoint, both of these methods produce the exact same root locus, and therefore the exact same stability of the system. But the important thing to remember though is that in both of these situations we started from this basic form for drawing root locus, 1 plus k times g of s equals 0, and this is important to start from. But if you watch my last video on the introduction to the root locus method, you'll notice that I use this equation instead, which isn't in the form that I just mentioned. Well, luckily getting to that form is pretty straightforward. Remember that you're looking for the roots of the characteristic equation, and you want to see how those roots move as k is swept from 0 to infinity. Once you set this equation to 0, we can start to put it in the correct form, and we can do this in 2 steps. The first step is to group all of the terms involving k together, like this. Then you can divide out this first part, the ones without k in it, and you're left with the form of the characteristic equation that is in the exact same form as the one from above. And so now s over s cubed plus 4s squared plus 1 is the new g of s of the system. So just like we did in the last video, using this method allows us to see how varying any parameter in the system affects the location of the poles, not just how gain in the feedback path affects it. So this is really powerful. Just reorder your characteristic equation into this form and you're all set to go. Okay, so I've made my plea for why you should learn this, and then I've explained how to set up the characteristic equation to start drawing the root locus. And I apologize for rambling so long in this video and not making it to the actual root locus drawing part, but we're going to start that right now. So that I don't keep you in suspense, I'm going to tell you that I'm going to present 10 different drawing rules. Now you'll see in different books they're going to have a different number of rules, but I like it as a 10 rule set. But don't let all these rules scare you off. Most of them are ridiculously simple. And once you practice the rest a few times, you won't even have to think about them. They're just going to come naturally. Now I'm only going to present the first 4 in this video so I can keep it short and hopefully interesting, but the rest I'll go over in the next video. So let's get to it. Remember that we always start from this form of the characteristic equation. 1 plus k times g of s equals 0. And instead of writing g of s, we can just write it as the ratio of 2 polynomials, q of s in the numerator and p of s in the denominator. So if we look at what we did before, q of s would just be s, and p of s would be s cubed plus 4s squared plus 1. Now why we break it up like this will make a lot more sense here shortly. So rule number 1 states that there are n-lines, or loci, where n is the degree of q of s or p of s, whichever one is greater. This just means that there are as many lines as there are either poles or zeros, whichever one you have more of. And this is going to make a little bit more sense here after I explain rule number 2. The second rule states that as k increases from 0 to infinity, the roots move from the poles of g of s to the zeros of g of s. Let me explain this one a bit. We can start from the basic form of the characteristic equation and then multiply both sides by p of s to get this new equation. Now let me plot the poles and zeros of just some fictional g of s in the s-plane. Remember that the poles of g of s are when the denominator, or p, equals 0. I'll just make up a couple locations here in the s-plane and mark them with x's. These are the poles of g of s. And the zeros of g of s are when q of s, or the numerator, equals 0. And I'll just put a 0 right here just for this demonstration. Okay, so now we can go back to this form here that I'm circling and say what happens when k is 0, or at the beginning of the root locus. Well, in that case, q of s goes to 0, and all you're left with is p of s equals 0. But remember, these are the poles of g of s. So when k equals 0, the poles of the closed loop system start at the poles of g of s. And as k starts to approach infinity, you start putting more and more importance on q of s. And so eventually it comes to dominate the equation, and so as k reaches infinity, the root locus ends at the zeros of g of s. And this is exactly what rule number 2 says. The closed loop poles of a system move from the open loop poles to the open loop zeros as k is increased from 0 to infinity. So then you might ask, what happens if there's more poles than zeros, or more zeros than poles? Where do the lines travel to and from then? Well, let's start with an easy example. If there are the same number of poles and zeros, then they each have a pair, and the roots travel from one pole to one zero. And if there are more poles than zeros, then the lines from the extra poles will go off to infinity. So you can see in this example that there's one pole-zero pair there in the center, and then that extra pole, its line goes off to the left to infinity. And the reverse of that, if there's more zeros than poles, then the extra lines come from infinity. Now I like to think of this as each open loop pole has its open loop zero friend, and they draw a path between the two. And if a pole or a zero doesn't have a friend, then they go off to infinity searching for them. Alright, enough of that. On to rule number 3. When the loci are complex, they always occur in conjugate pairs of each other. So you might already know this or have noticed it when you're looking at the poles of a system. But when you're dealing with real time as opposed to imaginary time, this is always the case. If you have at least one pole that's complex, you're going to have the conjugate of each other. You'll never have this situation here on the right where each pole doesn't have a complex conjugate of itself. So if you see that, you know you've done something wrong. And this brings us to the 4th rule, which is the final rule for this video, which states that at no time will the path that the roots take cross over themselves. This basically means that no value of s will correspond to more than one value of k. So you'll never have some crazy looping path like this, because you can see that the same path crossed over itself. However, if you have 2 roots on your root locus, and those 2 roots happen to cross over each other, this is perfectly fine. This rule is only for a single path to cross over itself. So those are the only rules that I wanted to cover in this video. But let me give you one quick demonstration of these first 4 rules so they kind of sink in. Let me start with this S-plane, and I'll just pick some random pole and zero locations. Now notice that we have more poles than zeros, and there's 3 poles, so we're going to have 3 separate lines. And now 2 of these lines are going to end at infinity because there's only 1 zero. And if I label these 2 roots over here as A and B, these are complex conjugate pairs of each other. So as you draw the lines in this root locus, just know that these are going to move in pairs, or mirrored about that real axis. And finally, the 4th rule just states that none of these root paths are going to cross over each other. And if I draw the root locus for this system here in this light blue, this is the way that it's going to look eventually when we learn the rest of the rules. So don't worry if you're confused right now. Hopefully we'll clear up that confusion in the next video. But right now, just be thinking about these 4 rules when you look at a root locus plot. Start to notice how many open loop poles and zeros there are, which lines go to infinity, and which lines terminate at a zero. Also watch the complex roots and see how they move together with mirror symmetry about the real axis. And finally, notice the structure of the lines and how they never loop back over themselves. By paying attention to these details, you'll start to be able to visualize how a root locus will look just from a map of open loop poles and zeros. And like I said before, this understanding of how closed loop poles move will make your job of designing a controller in the S-plane much easier. So don't forget to subscribe if you don't want to miss any future lectures, and you can follow me on Twitter at Brian B. Douglas. And if you want, you can leave a comment or question here in the section below or on Twitter, and I'll try to get back to you. As always, thanks for watching. We'll see you next week.